Hi, everyone, and welcome to our final project presentation. For our topic, we chose to calculate statistics on donations to U.S. election campaigns. My name is Mita Gure, and I am joined by my partners, Christian Aldover and Xiaolong Li. So first, Xiaolong will give us a little background on this topic.
Hi, I'm Xiaolong. First, I want to talk a little about what this project is about and why it is important. Campaign donations have come under increasing scrutiny over the past few years because of the abuses to the system that have come to light recently. For example, tech money, which we have begun hearing more about. Tech money is money donated to election campaigns that does not need or get to be reported in that candidate's FEC filings. One way to do this is the case of nonprofit corporations who are able to legally make issue advertisement endorsing or rejecting a candidate by name as long as they do not tell their viewers to vote one way or another. In the 2008 presidential election, non-disclosed spending hit a record about $78.8 million. In some cases, even when that money does get disclosed, there are still hidden intentions behind it, such as in the case of Super PAC. It's possible for a candidate to make donations to Super PAC supporting themselves through corporations that they own. Corporations are even able to donate to candidates with the intention of getting legislation that benefits themselves. It's important for citizens to know who their candidates get money from in order to know where their interests lie. All of this information is public record on fec.government. You can search whichever queries you want, and maybe even find out where your district's congressperson got campaign funding from. For this project, we decided to focus on three queries specifically. First, what are the sources of candidates' maximal campaign donations? Second, how much does each state contribute in total to their candidates' campaigns? And finally, how much money do candidates report as contributing to their own campaign? Now we collect candidates' information for different campaign years are in different fields. Every line of dataset is formatted as value 1, 2, and 3. We use Spring.Split to divide each line into an array of strings for ease of finding specific data values. And we choose MapReduce because of its increased accessibility over Peg and Hive, as well as the amount of control it allows in processing large unstructured data systems. We also used 3-node Hadoop cluster of AWS Medium instance, where the name node also functioned as a data node in order not to waste processing power. Now, let my groupmate Mita tell us how this application implements.
Thank you. So before we begin talking about application design, I just want to quickly go into how MapReduce applications work. So first, the input data is split by file. Then each file enters the extended map class, where it is processed, shuffled, and sorted. The map method gets run concurrently on multiple files to speed up execution, so it must be thread safe to avoid updating the wrong variable. Once you have completed processing the data in the map method, you write a key value pair to the context to be reduced by the extended reduce class. The reduce method within the reduce class organizes and collects the data from the map method, and the result is your output. So now we can talk about how I designed the programs. The first class determines how much each candidate spent on their own campaign, the candidate contribution. So the mapper class calculates the percentage of each campaign that was funded by the candidate themselves, which is a value in the candidate record that was from the dataset. the class writes a key value pair containing a range of percentages and a counter to the context. Then the reducer class takes this input and it sums the key value pairs for every key to find out how many candidates funded their own campaign at each contribution level. Our second class determines what kind of donation constituted the maximum for the candidates and adds them all up. We want to find out how many received the maximum amount of donations from individuals, from political committees, from party committees, and so on and so forth. So the mapper class creates a double writable array containing the value of each category for the candidate. It finds the category with the maximum value and then writes a key value pair containing the maximum donation category in a text object and a counter in an int writable object. And then the reducer class takes this input and sums the records to find the number of candidates that have each donation category as their maximum. It's important that the map class is thread safe. So the method that we used was to create an array of values, sort that array so that the max value is on the end, and then test each variable in the array to know which one is equal to the maximum value. So in class 3, we find the total amount of money that was contributed to candidates by private citizens in each state in the US. The mapper class writes a key value pairs of estates in a text object and donations in a double writable object from individual contributors to context. And again, these are all taken from candidate records. The reducer class adds the total donations from each state and outputs a key value pair containing the state name and the total amount that people in that state donated to election campaigns to context. So as you can see from this data, we divided percentages into increments of 10% because there were very few candidates who funded between 10 and 90% of their own campaigns, and we wanted to make the data easier to read. This chart shows the percentages of candidate contribution to campaign funds from the campaign year 2015 to 2016. So 20% of candidates funded almost the entire campaign, while 80% funded either none or very little of their own campaign. Our second class's output is shown here. As you can see, the majority of candidates were funded by individual donations, followed by party committee contributions. Comparatively less were funded by loans, political committees, or themselves, which makes sense because these donations would be harder to get than individual donations. So finally, for this graph, I didn't count candidates from US territories to keep the output simple. Then for every candidate, I created a key value pair of that candidate states and how much they received in individual contributions, which was added up in the reduce phase. As shown by this graph, Florida has the most campaign contributions out of any state, and New Jersey is rather on the lower end of the contribution scale. This graph does not account for population size or the amount of constituents that each candidate has, just total contribution from that state in the year of 2015 and 2016. So now my group mate Chris will talk a little bit about how we evaluated these programs for load balancing and fault tolerance.
Thanks, Mita. So, of course, it's important to talk about our evaluation, our analysis on scalability as a function of the cluster size and data size, and also the performance degradation in the presence of node failures. Our evaluation makes use of the MapReduce job tracker, which is port 8088 on the name node instance, and the Yarn node manager. We varied the size of the input data in order to test load balancing. We also varied the number of data nodes available for processing to see if performance degrades gracefully in the case of the node failures. And to top it off, we measure performance by seeing how long the entire job took to complete. That is the sum of the time required for the map test to complete, along with the reduce task. In the following slides, I will talk about this more in detail. So for evaluating the scalability of our programs, we add one more file at a time and measure the total amount of time taken for map and reduce tests. The program scales gracefully because as we add files to the input, we could see that the percentage increases in execution time, and execution time remains the same. In order to evaluate fault tolerance of programs, we decommission one node at a time and measure the total amount of time required for each of the jobs to complete. We update dfs.replication in hdfs site.xml to reflect how many nodes that will be in the service. We also add the host names of data nodes to be excluded in user local Hadoop exclude to tell Yarn not to give these nodes any jobs. And as you can see from the graph, each addition and subtraction of a data node still lets the programs run efficiently. Losing 25% of the processing power is going to cause roughly a 25% slowdown, and likewise, 50% processing power loss also caused a 50% slowdown. So therefore, we conclude that our applications will degrade gracefully in the case of node failure. Using our project application as an example, we can conclude the following. MapReduce allows us to process enormous distributed datasets with relative ease. Cloud computing gives us the resources to run extensive computations on multiple machines, which makes the process take less time. The relative simplicity of the MapReduce tools, along with its raw processing power, makes it a very useful and powerful tool, and it's no wonder why MapReduce is growing so rapidly. And this has been our presentation. Thank you for listening, and we hope you enjoy your summer.